This is Living Planet. Should we cross the street?
Yeah,
okay.
Let's go towards the river.
Towards the geese. Okay, so I'm walking with Neil behind Deutsche Welle. We're going on a walk. Neil, do you know why we're going on a walk today?
To look at the ducks or the geese over there? I don't know.
Not quite. Okay, so here's the thing. I wanted to test your knowledge of carbon dioxide.
You know I love being tested. It's so much fun when you run those tests on me because I always come across like, well, never mind.
Okay, so we talk about carbon emissions all the time. Really quickly, if you could name several emitters just from where we're standing. Yeah, we're kind of near a road, we're near the river. What catches your eye first as a carbon emitter?
Cars, shipping on the river, buildings, yeah.
Expound on that.
Heating.
Yes. Good job. Good job. Okay, so the point of this question is it's kind of everywhere we look, right? And do you happen to know off the top of your head how much carbon dioxide the world pumped into the atmosphere in 2024? If you had to guess.
Oh my God. If I had to guess, something between maybe 20 and 50 billion? I don't know.
So we don't have the exact figure for 2024, but according to the Global Carbon Budget, which is this UK initiative of groups of scientists from across the world that track carbon emissions, in 2024 it would have been 41.6 billion. That was the projection. But now a kind of personal question. So when I hear numbers like that, I just think, okay, yeah, that's a lot, but what exactly does that mean? Like, does that number hit you emotionally?
No, it's abstract. I mean, what do you do with that number? I wouldn't even know. I mean, just imagine now if it were a balloon and you filled it all with all of that carbon, how big would that balloon be? I have no idea.
Yeah, I don't know either. And so I was just thinking, we talk about carbon emissions all the time, and we take it for granted that we all know what that means. But I wanted to do a little more digging into that because even though I know what it means at an abstract level, somehow it doesn't feel enough. Do you know what I mean?
Yeah. A more direct approach, I think, would help if we could gauge that better. Maybe we'd be more conscious of what we're doing and how much we're emitting. Because in Germany, I think it's about 10 tons, the average citizen per year. How much is that? What does that mean?
Yeah, and I mean, we're also talking about how in the EU, carbon emissions have been going down since 1990. In other parts of the world, they're going up, like in China. And yeah, so I've been doing some digging, and I even found somebody who has a direct link to the first person who really started measuring this. And I wanted to know why, and if they could tell me, what exactly do we mean by saying 1 ton of carbon dioxide? I get it in an abstract level, but could somebody explain that in a way that hits me emotionally?
Okay. So by the end of this, will I know how big that balloon is?
Potentially. Potentially.
Because that'd be interesting. I really would like to know that.
How big that balloon would be. Okay, I'll add it to my list of questions.
Great.
Okay, should we go back in?
Yeah, let's go.
This is Living Planet. I'm Kathleen Schuster. To start off, let's break down these huge numbers for carbon dioxide to just 1 single metric ton. What would that look like? There are lots of analogies out there. For example, here's one from MIT. Imagine a cube that's about 8 meters tall, 8 meters wide, and 8 meters long. For US listeners, that's about 27 feet. So if you emitted 1 ton of CO2, it would take up about as much space as that very big 8 by 8 by 8 cube. And what exactly emits 1 ton of CO2, you might ask? According to that same estimation, it would be flying from Boston to London or driving a gasoline-fueled car for about 3 months on a regular basis. There's a balloon analogy too, but we're going to save that for a bit later. So now that we have one way of picturing 1 ton of CO2, multiply that by 41.6 billion. That's how much the Global Carbon Budget estimates the world emitted in 2024 by burning fossil fuels. Hard to picture, right? What's even more mind-boggling is while the world is emitting too much CO2, carbon dioxide only makes up a really tiny percentage of the atmosphere, just 0.04%. Today, there's a wide consensus among scientists that carbon dioxide is causing rising global temperatures and disrupting weather patterns with catastrophic effects. But given how little CO2 is in the atmosphere, have you ever stopped to wonder why scientists even started tracking carbon dioxide levels in the first place? One person with some unique insights into this is a man named Dr. Ralph Keeling. He's a professor of geochemistry at the Scripps Institution of Oceanography at UC San Diego. A large part of his research is about oxygen in the atmosphere, but Ralph also has quite a personal link to the story of carbon dioxide, because in the 1950s, his father, a man named Dr. Charles David Keeling, made an important discovery. Today, the name Keeling is associated with two iconic CO2 symbols. The first one, which really only scientists will recognize, is the way he collected air samples.
And so he had really a simple approach, which was to have a glass flasks. These are spheres about the size of a soccer ball, then with a little opening on it, like a little tap. And in the lab, the approach was to just pump all the air out, so it was completely evacuated, so the air had nothing in it. Then you take that out to wherever you want to take a sample, and you simply open it, being careful you don't breathe into it, and being careful that it's not downwind of car exhaust or something. And then as you open it, the air rushes in, and you've thereby captured a sample.
Could you describe what it sounds like when you do that?
It sounds sort of like that.
The second symbol is what's known as the Keeling curve. If you've ever seen a graph showing rising levels of CO2, then you've probably seen it. Basically, it's a diagonal line with small zigzags that moves up steadily from just before 1960 to present day. It shows the rapid rise of CO2 in the atmosphere in parts per million. We'll come back to what parts per million means a bit later.
He had available to him new technologies to do carbon dioxide measurements in a different and better way than had been done in the past. Carbon dioxide, by the way, had been measured in air for centuries because it was recognized all the way from the 1700s that it had physiological importance for organisms, and so biologists were putting mice in bell jars and seeing what happened to the content of the air, and they had to measure outside to know what they were starting with and so forth. So there was a lot of work on this.
Skip forward from the 1700s to the end of the 19th century, and the Industrial Revolution and large-scale coal burning are in full swing. A Swedish scientist named Svante Arrhenius hypothesizes that burning fossil fuels could introduce enough CO2 to the atmosphere to cause world temperatures to go up. There are other scientists wondering about this too, but crucially, there isn't a clean and accurate way to collect the data. Not until Keeling, that is. And how he even starts down that road is a bit of a fluke, because originally he's at Northwestern University getting his PhD in polymer chemistry. Ironically, he could have just as easily gone into the burgeoning plastic industry, but he feels himself drawn to the American West.
And he was very interested in somehow having the outdoor experience be part of his life, and saw possibly a way to make that happen by moving into the geosciences. He took a postdoc at Caltech without any clear idea of what he was going to do. People were talking all sorts of things and ideas, and he eventually decided he would work on a project to measure carbon in rivers. Why, you ask? Because no one had done it. So it was one of these, okay, well, here's a frontier of science. Let's just see what's going on. One of the reasons it was fun was that there's no rivers that run year-round anywhere near Caltech, which is basically in Los Angeles. So he had to drive up and go to a beautiful place along the coast called Big Sur. So he got to go camping as part of his work. But in the course of that, he realized that an important control on carbon in rivers would be whatever was in the air. How much carbon dioxide was in the air would have a big impact on the river amounts.
And he finds out quickly there isn't any reliable data on atmospheric CO2, so he decides to make his own measurements in the pristine forests along central California's rugged coastline. That's where his glass flasks come in. He'd collect his samples, and then back at the lab would figure out how much CO2 was in there by freezing it out with the help of liquid nitrogen, which was newly available.
And that gave him a both very accurate and very precise measurement.
Little did he know that homing in so precisely on CO2 was going to lead him to some big discoveries.
And what he found to his surprise as part of this river project was that he was getting almost the exact same number, something around 310 parts per million, whenever he took a sample in the afternoon. Now, when he took a sample at night or earlier in the day, he would typically get higher numbers. But why this consistency in the afternoon?
This first discovery is that the planet is essentially breathing. CO2 levels go up and down naturally over 24 hours. That's because plants take in CO2 during the daytime and release it at night. If you take a close look at the Keeling curve, you'll notice the diagonal line is a little jagged looking. That's because CO2 levels also fluctuate with the seasons. They go down slightly in the spring as plants take in more CO2, and then rise again in the autumn as vegetation decomposes. Keeling didn't realize this all at once, of course. It took a few years and many samples for a pattern to emerge. But the first recognition was that no matter where he sampled from, the level of carbon dioxide was steady. And that was a big deal because at the time, scientists believed CO2 levels were more variable. But Keeling was onto something new.
He then got samples from mountaintops, he got samples from a ship, and he confirmed that there was this fairly stable level of carbon dioxide in air.
So this is happening in the 1950s. Keeling's research draws attention at a really significant time in scientific history. There are a lot of important names from that era, but for this story, Roger Revelle is one of the most important. Years down the road, Revelle will become one of the fathers of global warming, and Keeling's data will play an important role in laying the groundwork for Revelle and others who make the connection between fossil fuels and CO2 levels. You see, up until Keeling, scientists believed CO2 levels varied by location, but Keeling is getting consistent measurements no matter where he takes his samples. So he hypothesizes that based on this, there must be a core part of the atmosphere where CO2 is building up. So Revelle brings Keeling on board at Scripps Institution of Oceanography to test this hypothesis. He becomes part of a huge international project, and then Keeling kind of hits the jackpot in terms of research. A weather observatory has just been set up in Mauna Loa, Hawaii. He's invited to take measurements there, and he also starts taking samples from the South Pole, and over the decades gradually branches out. Today, his son Ralph, who we've been hearing from, is still overseeing samples from 10 stations from Alaska to Hawaii, American Samoa, New Zealand, all the way down to Palmer Station in Antarctica. And they still use glass flasks. We're going to fast forward here a bit. Keeling's data was key to a landmark report headed by Roger Revelle in 1965 that warned of carbon dioxide from fossil fuels as a potential global problem. The science behind that fits into our initial question about what 1 ton of carbon dioxide means. But before we get to that, let's take a look at where things stand now.
From the Los Angeles Times, this is Boiling Point. I'm Sammy Roth. I've been reporting on energy and climate change in California and across the American West for a decade. I'll be asking scientists, politicians, activists, and journalists the same questions. What are the challenges we face to building a better world? And what are the solutions we need to embrace, even when it's hard? Boiling Point will be available everywhere you listen to podcasts, starting January 16.
When it comes to scientists predicting what our climate future might look like, the Mauna Loa data and the other measurements it kicked off are crucial. That's how Dr. Heather Graven describes it. She's a professor of climate physics at the Imperial College of London in the UK.
We sort of need to understand where we're heading. We need to understand how the system is responding to the changes that are occurring, because currently we have about a 50% discount on climate change because only about half of our emissions are staying in the atmosphere.
The other half or so gets reabsorbed by carbon sinks like oceans and forests.
But that might change in future, and for us to understand any changes like that and to respond to them, we really need to continue long-term measurements and scientific research to improve that understanding.
Heather also has a Keeling connection. Ralph, who we heard from earlier, was her PhD advisor when she was at Scripps. Her work focused on how to tell the difference between naturally occurring carbon in the atmosphere and carbon dioxide put there by fossil fuel emissions. She was looking at what's called radiocarbon. It's produced naturally in the atmosphere and takes nearly 6,000 years to decay.
So fossil fuels, because they're millions of years old, they've been underground for millions of years, they don't have any radiocarbon.
This presence of radiocarbon was also important for a study she and her team published in 2024, showing that the role of plants and trees in sequestering CO2 might be different than previously thought. And they had another surprising source of radiocarbon to help them.
Another way that radiocarbon is quite useful is through the radiocarbon that was produced artificially by nuclear bomb testing in the 1950s and 60s. So when the bombs were exploded, they produced extra radiocarbon in the atmosphere. And so what we've been able to do through measurements is kind of track how that extra radiocarbon moved through the carbon cycle, so how it was taken up into the ocean and into plants and soils. And that helps us understand how quickly those exchanges happen and helps us understand how much carbon dioxide is also going into the ocean and into the plants and soils on land.
Scientists want to know if natural sinks like oceans and forests, for example, could realistically lower CO2 emissions in any significant way. Heather says plants and soil combined take up about 30% of our emissions, but she and her team wanted to know how long that 30% stayed locked away. So they looked at the radiocarbon from the nuclear bomb testing.
And so what we found is that compared to most current models, our studies showed that there should have been more uptake of this radiocarbon into the vegetation. And so that is telling us that the rate that plants are taking in carbon every year is actually faster than what we expected and about 30% faster than the sort of central estimates.
But plants taking up more CO2 isn't necessarily a good thing because it has to come back out.
And so basically, if you have more coming in than you previously expected and more coming out, it's not staying as long in the vegetation. And so that has implications for how useful any kind of land management or kind of tree planting activities are in taking up carbon, because our findings indicate that the carbon that's taken up that way is not going to stay around as long. So it's not quite as much of a stable reservoir to store the carbon, and it will be coming back out again sooner than we thought.
So now back to our original question. How can we wrap our minds around tons of carbon dioxide? First, it's important to understand how much is already built up in the atmosphere. Earlier, Dr. Ralph Keeling was talking about carbon dioxide in terms of parts per million. When his father started collecting his data, the world was at around 315 parts per million. Now we're at about 427. Meaning out of 1 million molecules of air right now, 427 are carbon dioxide. That might not sound like a lot, but today, CO2 levels are higher than at any point in human history. They've jumped by 50% since the Industrial Revolution began in the mid-1700s, when they were at around 280 parts per million.
So it's the most important greenhouse gas that's directly impacted by humans. You can think of, cholesterol is only a tiny component of your blood, but it has special properties. So it matters how much you have. So carbon dioxide has special properties.
One of those special properties is that it traps heat. Sunlight travels down through the atmosphere and gets radiated back up in the form of infrared wavelengths, which can travel past oxygen and nitrogen in the atmosphere with no problem. But CO2 molecules soak up the infrared energy. The CO2 vibrates and then shoots the infrared energy in different directions. Like Heather mentioned, half goes into space and the rest stays trapped on Earth as heat. Last year, Earth's average temperature was 1.5 degrees warmer than pre-industrial levels. That's about 2.7 degrees Fahrenheit.
Might not seem like a lot, but you only have to cool the Earth down by 5 Celsius to put us into an ice age. And we're nowhere near the point where we've got the system under control. So we're probably headed for 2 or 3 degrees Celsius warming at this point. So it's really pretty daunting. So I would say we're already in the danger zone, and we're moving faster than ever further into it. That said, there's never better a time than now to deal with this issue.
Keeling and other scientists say if we want to reach net zero, first we have to cut out fossil fuels, period. And then, he says, we need to scrub an additional amount of CO2 from the air to offset what continues to be emitted. In the US, the average citizen emits about 14 tons of CO2 per year. In the EU, it's about 7.5 tons per capita. That's according to UBA, Germany's Environmental Protection Agency. And what's already built up in the atmosphere isn't going away anytime soon, not for at least several hundred years.
Yeah, I mean, in effect, we're basically using the atmosphere as a landfill for our CO2, and we're dumping an awful lot in there.
So to keep this landfill from growing, it might actually help to be able to picture how much an individual emits within the span of a year. Ralph was kind enough to provide an analogy that was neither a cube nor a balloon.
Let's suppose, how big is the world? I guess that's the question. And one way to think about it is to divide it up among all the people in the world. There are about 8 billion people in the world at this point. And if you divided the whole surface area up, you'd have something like 15 acres per person. Now that would, on average, include ocean and land.
How much is 15 acres, you ask? It's about 3 New York City blocks.
So let's suppose we all have our own little patch of the planet. And that little patch, or that little hypothetical microplanet that you have would have had something like 270 tons of carbon dioxide in the air naturally. And we're emitting around, in America anyway, the Americans are emitting about 14 tons per year.
So in this scenario, this person is pumping 14 tons of CO2 per year into their own personal atmosphere by driving a car, using electricity, etc. The second year, their emissions double to 28 tons in total. The third year, they're at 42 tons. It adds up really fast.
So you can see that it would take about 20 years to double the amount in the air.
Of course, not everyone is emitting that much. According to the International Energy Agency, the average North American emitted 11 times more energy-related CO2 in 2021 than the average African, for example. But unlike in Ralph's hypothetical of our individual atmospheric bubbles, these emissions have wide-reaching consequences for everyone on Earth, because only about 10% of the world's population is responsible for nearly half of its emissions, carbon dioxide being the main greenhouse gas.
We can't pretend we're innocent anymore and we're just going to live in the earth the way we had it. The earth is changing because we made it change, and we have to get ready for all this. And so tracking what's happening and keeping up with things is really vital. And I mean, as someone in that field, it is exciting. I mean, it's exciting in the same way that you can imagine in a military campaign, you're the scout going out there to see what the enemy is doing, and you see, oh my gosh, they're coming over the mountain. So you race back and give the news. Well, that's scary, but it's also exciting. And so that's the kind of mix I see myself in at this point.
Okay, so Kathleen, coming back to the top of this episode, my question, right, it still hasn't been answered. That balloon. How big is that balloon, for a ton of CO2? Did you get that sorted?
Okay, yes, I did. Okay, so according to NASA, if you had 1 ton of CO2, that would fill a balloon with a diameter of nearly 10 meters. Okay, or that's 32 feet for people like myself who still think in feet mainly. So that's about half the size of a regular hot air balloon. There you go.
Now I can see it. Now I can see that ton of CO2.
Do you know, I had this argument with my husband last night about whether this is a helpful analogy or not.
I think it is. You don't think so?
It does nothing for me. I have to say, after researching all of this, the visual of 1 ton of CO2 as a gigantic cube or as half the size of a hot air balloon or, I don't know, an elephant, whatever. Like, it doesn't, how to put it? I don't want to be misunderstood here. I think it's really important to be talking about CO2 in tons to understand, we're talking about billions of tons. That's very serious. But I don't have that emotional connection to, oh, this is a crisis in the same way as, like, for example, if you have an oil spill, it's something you can see. It's not supposed to be in the water. It's tangible. But CO2, for all intents and purposes, it's a gas and it's invisible. So I don't know, something with my brain, it just doesn't work for me.
Well, I'm the exact opposite. I love the visuals. In fact, actually, because I wasn't sure whether you would, answer that question about the balloon. So I did some research myself for this. And I've got some more number crunching for you. Just bear with me, please. I'll try and be as quick as possible.
Okay.
So according to your maths, right, in the script, you had like 1 ton of CO2 is a cube that is 8 by 8 by 8 meters, right? Which would give us 512 cubic meters.
I'm already falling asleep, Neil.
Now, wait a minute. Now, if you stacked 1,953 of those cubes, if you stacked them, you'd be able to fill the Empire State Building once. Approximately, that is, right? I think everybody's got a picture of the Empire State Building, right? Now, just coming back to the... No, let me blow this balloon up, so to speak.
Oh, yeah.
So the US had just under 5 billion tons of CO2 emissions in 2024. And just to make the maths easier, let's go with roughly 2,000 tons of CO2 equal 1 Empire State Building, right, in terms of volume. So then the US emissions in 2024 amounted to about 2.5 million Empire State Buildings that are cluttering up the place, right? And then you'd need to multiply that by 8 to almost get the 41.6 billion tons of CO2 that the world emitted in 2024, which would then be the same as 20 million Empire State Buildings. Now, I also did something else. Just one more, because I also went
Let
into...
it out, Neil.
I went into... I used ChatGPT for this last one because I was just wondering, with the volume and all that. I don't know, it was night. I was looking at the moon. and I was just wondering how much CO2 would fit into the moon, right?
Stop.
And I fed this into ChatGPT, and the answer was, and now I'm quoting ChatGPT, the world would need to emit 43.2 quadrillion metric tons of CO2 to fill the volume of the moon, and at current global CO2 emission rates, this would take about 1.15 million years to do. Now, that may sound really long to us, right? But I think that figure's quite strong, because if you think about it in planetary terms, that's actually quite short. Okay, I can see Catherine's in despair here. She's putting her hands over her eyes. She can't listen anymore. I'll leave it there.
No, actually, I really appreciate this. And I'm sure the listeners out there...
I'm not sure you do.
No, I do, because I think it still comes back to the beginning of our episode quite well, which is the part of me that goes, yeah, so what? I mean, like... And that's not to say, again, I don't want this to sound like I'm saying these emissions don't matter. They matter very, very much. And talking about, we've put 41.6 billion tons of CO2 into the atmosphere. That's a very big deal.
In 1 year.
In 1 year, yeah. That's a very big deal. But I think my point is more just these analogies really get me, because I'm like, why does it's just not making anything in my brain go, oh, okay, I can really feel the emergency here. But I think what did it for me was when Ralph was like comparing it to cholesterol, because it makes up such a minuscule part of the atmosphere, which is where a lot of, I think, climate deniers also jump in and say, oh, it's only 0.04% of the atmosphere. And, anybody who's unfamiliar could very easily say, oh, yeah, well, that doesn't sound like a big deal. But yeah, just like cholesterol, a teeny tiny bit of cholesterol can kill you. And this is causing a huge imbalance in a system where carbon dioxide is naturally in our atmosphere, but we're adding way too much. That's why it does actually matter quite a bit if the country you live in has good green policies, or if they don't care about green policies. And there are a lot of countries moving back in that direction as well, saying it doesn't matter. And it very much does matter. And I think also, Keeling, he was also very clear and has been clear in previous interviews saying, even if we do cut all of our emissions, like if we manage to get to net zero, that's just keeping things from getting worse, which is
just turning off the tap.
Yeah, exactly. Which isn't a happy message. And then it's like, okay, and then how do we get the additional CO2 out of the atmosphere? But it's fascinating. This is something we hear about so often, but there's still so much to say about it. And Yeah, and there was actually one thing that didn't make it into the episode that I did want to bring up for people out there who are really interested in history. I highly recommend looking into this other scientist who was brought up named Roger Revelle, for people who aren't already familiar with him, who was one of the leading scientists in the States who brought attention to the issue of global warming. And he was the one who got Keeling into this huge international project in the late 1950s called the International Geophysical Year. And I don't know about you, but for some reason, I don't think I had ever heard of it, or I think I've heard of projects associated with it because it kicked off the space race, which I didn't really realize. But it was this huge project of like 30,000 scientists, like almost 30 countries involved, that really paved the way for a lot of research about how the Earth works, how the poles work, how like the relationship between the Earth and the sun. And I really fell down a rabbit hole of research when I was doing that. And I came across a really intriguing fun fact, which was that...
I can tell you're dying to tell me
I am dying to tell you this, which is that Roger Revelle was a professor to a really important U.S. politician who later became a huge advocate for climate change. Would you like to guess who it is?
Well, I can only think of one, really.
There's only one.
Is it Al Gore?
It is Al Gore.
Wow.
And he claims him as like a huge influence and mentor in his life because he took a class from him in the 60s when Revelle started teaching at Harvard. And he was at that time working on issues to do with like population growth, because that became another huge source of area of research for him. And this is why this became a huge part of Al Gore's work from the beginning, because, you know, he became a politician in the 70s and at a very young age, actually, for a politician, and kind of rose through the ranks. But climate change was a big part of his message. And I also fell down a rabbit hole of research there and started watching like interviews with Al Gore from like 1992, where he's talking about this. Okay. That poor man has been going on and on about this for decades.
Well, I think some people are listening.
Yes,
I hope some people are still listening to this too. If you liked this episode, be sure to scroll back through our feed. There you'll find episodes about the suspicious world of carbon offsets and the promise and pitfalls of carbon capture technology. You can, of course, find Living Planet wherever you get your podcasts. What did you think of this episode? Send us an email to livingplanet@dw.com. Our sound engineers were Jürgen Kuhn and Michael Springer. Living Planet is produced by DW in Bonn, Germany. Before you go, we've got a podcast recommendation for you. I Know Dino, the Big Dinosaur podcast. Studying dinosaurs can teach us about the prehistoric world, but also the world today. Climate models of dinosaur ecosystems help us understand global warming. Studying dinosaur diets can help show the link between plant and animal evolution. A new episode of I Know Dino comes out every week with new dinosaur discoveries you won't hear about anywhere else. You can find I Know Dino on Apple Podcasts, Spotify, or wherever you get your podcasts.